Ever wonder how neural networks really learn? Like, how do they turn raw data into smart decisions? Well, researchers just cracked a big piece of that puzzle with something called the features at Convergence Theorem, or FACT for short. Let's break it down. Neural networks are these complex systems with layers of weights that process data. But understanding how they learn features, like recognizing edges in images or patterns in numbers, has been tricky. Traditional methods focus on tracking how weights change during training, but that's like trying to understand a recipe by watching a chef mix ingredients in real time. It's messy and hard to generalize. Enter FACT. This theorem gives us a snapshot of what's happening when a neural network finishes training. It shows that at the end of training, the network's weights follow a specific mathematical rule. Think of it like a fingerprint. The way the weights are arranged relates directly to the data they've seen and the errors they've corrected. Here's the core idea. When a neural network is trained with a technique called weight decay, which helps prevent overfitting, its final weights satisfy an equation that links two things: the inputs it processed and the gradients it learned from. In simpler terms, the network's feature matrix, a way of representing what it's learned, is shaped by both the data it saw and the mistakes it made. This isn't just theory. The researchers tested this on real-world datasets like MNIST, handwritten digits, and CIFAR-10, color images. They found that the predicted feature matrix from FACT matched the actual weights almost perfectly, with correlations as high as 0.999. For comparison, other methods like the neural feature ansatz, NFA, fell short, especially in tricky cases. But here's where it gets even cooler. By tweaking an existing algorithm called recursive feature machines, RFM, to follow FACT, they created a new method called FACT-RFM. This baby doesn't just work well on tabular data like spreadsheets. It also mimics behaviors seen in neural networks, like grokking, sudden understanding of patterns, and phase transitions, sudden shifts in learning. It's like giving a neural network's brain a new set of tools to think with. So why does this matter? FACT gives us a clearer lens to study how neural networks learn. It bridges the gap between theory and practice, helping us design better models and understand why some techniques work. Whether you're a student, a researcher, or just curious about AI, this is a big step toward demystifying the black box. Next time you see a neural network solve a problem, remember, behind the scenes, math like FACT is making it all possible. Thanks for watching. Stay curious. Ever wondered how AI models learn from context, like picking up patterns in a conversation or solving a math problem on the fly? Today, we're diving into a fascinating area of research that's rewriting the rules of neural networks. Imagine you're handed a quadratic equation like f(x equals x2) or something more complex. Now here's the question: what's the simplest neural network that can perfectly mimic